Aliens or NSA? Okay, and then they get pulled into the solar system. So the population of comets at one point was huge inside of the solar system, right? And then they get either then put into these elliptical orbits like Churyumov-Gerasimenko, our comet, or they get ejected from the solar system into, what do we call it, an Oort cloud. Okay, so we have this one comet, and this is our comet. It's called Churyumov-Gerasimenko 67P. 67 because it was 67th comet discovered, and P because it's periodic, right? And, you know, so comets go like this sometimes. So they go, there's perihelion here, here's Earth, here's Sun, here's Mars, right? So the comets go on these elliptical orbits. They are frozen. This nucleus is frozen over there, and we can't see it because it's very dark. Comets are like twice as dark as asphalt, okay, and small, so you can't see it. You can't do anything with it. And then they come here and they blind us because of all this emanating dust at the perihelion. Some of them come close to the sun and they disintegrate or go into the sun, you know. So it's very difficult to manage these comets. Okay, this is a 6-year period. So we have to land on the comet when it's still cold and there's not too much dust coming out, and but not far away that we don't have power on our spacecraft. So it's a fairly difficult problem. So if you want to interrupt me with any questions, please do. This, you know, that's so you know, so you have to build a mission to land on a comet, right? And so you have to design a spacecraft. And you know, if you work for NASA, you work at a company that has a contract from NASA, this is what you would do. The only problem is, you know, that it's 1 pixel there, okay, and you don't know much about this comet. So, you know, it's like they tell you, okay, pack your suitcases, we're going on vacation. And they don't tell you if it's Florida or it's North Pole, right? Different problems. So one of the things, so what do you think? You know, they ask you to build a spacecraft to land on a comet. What are the first things that you have to consider? What do you have to land on something? What is the most important thing if you want to land on something? Can I have a volunteer here? Okay, can you come up here for a second, please? Okay, right? If what's your name? Thomas. If Thomas is walking, right? So start walking, not too fast, but and I got a job to catch up with Thomas, right? And grab his hand. What do I need to do? Okay, first to see him where he is, right? Then what else? If I okay, keep on walking, right? If I do this, right? Thomas is walking, Fitbit is working. Okay, keep on. And I go like this. Hey, is this a good way of catching his hand? No. So what do I have to do? Okay, start walking the other way. You're at the aphelion, so go back. This is a very elongated trajectory. Okay, what do I have to do, right? Figure out, you know, basic vectors, right? I have to figure out his direction, right? And then what else? What are the 2 parts of vectors? You see, that's what I'm saying. Very basic stuff.
Move a little faster.
Magnitude, right? Magnitude and the direction. Big hand for Thomas for his very professional. And Thomas, okay, I told you I'm going to help you get. I don't know, Thomas, what field are you in?
Computer engineering.
Computer engineering, but you know, if you're on this side, he's a good-looking guy. Maybe he would want to do some modeling. Thomas, could we have more swag in your walking? Okay, so try it again with more swag. You're on a runway, Thomas. No, you know.
Modeling.
You know, let's try this. All right, big hand for Thomas. Great, Thomas, thank you. Excellent. So send me an email after your first professional modeling job. But it may be modeling of the solar system. Okay, so that's what we have to do. You have to find magnitude, right? and you have to find, you know, so, right? So it's like getting on the bus. I actually, you guys don't understand it here, but I came from Poland. You see, in Canada, bus drivers have the courtesy to stop at the stops, at the you know, stops. In Poland, they don't. You know, they kind of slow down. So you understand the concept of magnitude and direction very well because you have to run and, you know, and you have to help they open the door for you, right? So that's how it is here too. So yeah, and you have to understand the speed of the comet. Unfortunately, most of the time, and this is a page from this high school physics book, right? So conservation of angular momentum, and I'm telling you, there's really not much more than this, you know, this one equation to figure it out pretty accurately. Yeah, they're gonna have 3-body and 4-body and 5-body problems, and they add, you know, gravity of the sun and the Jupiter to this. But for the most part, you know, you have to just figure out what your speed is. This is click on this. Okay, so look at this. This is our comet, right? And you see it in a background of stars. Let's see one more time. Okay, so now you have some estimate of velocity. It's kind of tricky because you don't know, you know, exactly the perspective, but that's how you figure out the velocity and magnitude. But usually you know it at the perihelion because that's where you can see it, right? So that's a little bit of a problem because at the perihelion the velocity is different, and we measured it to be. You can read it. What is it? I don't want to run again there. At the perihelion, what, 100? Yeah. So let's say you know this speed here, right? But I told you that we don't want to land here because the comet is extremely active, right? So you can't land. So you have to land, and we decided we land at 3 AU, exactly, right? 3 AU. So if you know that at 1 AU the speed is this, how do you figure out what's the speed at 3 AU, right? Well, right, angular momentum conservation, right? MVR. Right? So, and then you get a simple result, you know, from this just one equation that says you're going to be landing at 54,000 kilometers per hour. You know, that's something like 3 times the speed of a bullet. So, you know, so you have a bullet, and you have a mosquito, you know, trying to fly alongside the bullet and then hop on it, you know. And you're directing this from Edmonton, and your bullet is in New York. You know, so, and there's 28 minutes of communication in between gap, you know, because that's how long it takes for the radio signal. Not, but the other problem is it's 54,000 kilometers an hour, but another problem is that we don't have a rocket that would propel the spacecraft to that kind of a speed. It's just, you know, you can strap maybe 4 Apollo Saturn rockets, but, you know, that's not feasible, right? So, you know, so what do you do? So this was our trajectory, okay, and you get a headache. I had it, you know, spacecraft follow this, but just looking at it, you get headaches, so I decided to just have a chart. But what we have to do is have a gravitational kick from Mars and 3 gravity assists from Earth. So this mission took 10 years to get to the comet, okay? So a lot of patience, you know, and then we can get to 54,000 kilometers an hour, right, from these gravity assists. And you guys understand what gravity assist is. I like to think about it like if you have all of you in your spare time go gambling, right, to casinos. Are the casinos here or they're illegal? Yeah. Okay. So tell your parents that you need some money to go to casino because this guy from NASA came here and asked you to do this experiment. Okay, and you look at the roulette wheel, and when they are spinning it, toss a ping pong ball at the edge of the spinning roulette wheel, right? So the spinning roulette wheel is like gravity of the rotating Earth, let's say, or Mars. And what's going to happen to the ball? What's going to happen? Slow down, it's going to sit there, it's going to happen something else to it. A ping pong ball that you toss it at spinning roulette wheel, right? What's going to happen? Yeah, well, fly out and change the direction, right? And it's going to fly out. It's exactly what happens to the spacecraft when you do it 4 times and you get your speed. Plus, the spacecraft is like a big tanker. You know, half of the mass of the spacecraft is fuel, because you don't know exactly that the speed of the comet, right? So, yeah. So you build your spacecraft. Okay, you can build your spacecraft to kind of catch up with the comet. That's okay. And then you build your lander. Well, lander is, I told you, this 1 pixel. Go and land on this, whatever it is. Is it concrete? Is it 2 meters of dust? Right? So we built this spacecraft. It shows how we launched it. And actually, the original rocket. Yes, question.
What percentage of fuel did you have left after all the gravity boost to correct for any?
Yeah. So what percentage? He's asking what percentage of fuel we had left. Well, right now we have maybe only a couple percent left. Very little. The firing of the thrusters that we had to do was to catch up with the comet, because we did not know it very, very well. And also, the speed of the comet changes depending how it shoots out the jets and changes its mass, right? So, so we had to do one of the largest delta V's, we call them, in the history of the space program. And that took a lot of, just that one burn took about 70% of the fuel. Now we have just a little bit left. Yeah. Anybody else? Yeah. It's something we have about 1,000 kilograms of fuel on board of the spacecraft. So, okay. So, this was the best picture of Churyumov-Gerasimenko, discovered by 2 Ukrainian astronomers, Churyumov and Gerasimenko. And I met Churyumov some time ago, and his biggest problem is that people call him Russian. I'm not Russian. I am Ukrainian. Russians are bandits. He always says. So don't ever, if you run into Churyumov, or Alan was good, because Alan knew everything about me, didn't call me Russian also. He knew I'm from Poland. He did his research. And actually I told him this, guys. So this is one thing. I'm sorry I deviate from my comments. But what he did was really excellent. And you have to do this, because you're concentrating on your equations, you're concentrating on your material, your tests. And at some point when you get a job, and your professors can tell you that too, you can be the most brilliant person, but you have to have human skills, okay? And you have to understand human psychology, okay? And you have to talk to sponsors, venture capitalists, or, NASA headquarters. And if they don't like you, well, you have to be, you better be Nobel Prize material, because otherwise you ain't getting no money, okay? So what Alan did was very smart. He knew about me, he investigated me, checked my credit report. No. But he knew how to talk to me. And that's what you have to do. Because sooner or later, I'm in management now, right? I'm the manager of the mission, started as an engineer, it was really exciting. But eventually you want to be in management or some kind of supervisory position, because you're going to get tired of all these stupid people telling you what to do. You say, I'm smarter than them, how come, So, but to get there, you have to know how to work in a team, you have to know how to talk to people, you have to read people, So don't, dating is a good preparation for this. So I'm giving you a good opening line. You see a cute girl in the cafeteria say, well, I'm doing my engineering experiments, so could we maybe go out? Because I have to work on my human skills. Original opening line, right? Okay, so we're trying to see what this body is on which we're landing, and we looked at it with Hubble, and we got this, and I got 3D print of this, right? So it kind of looked like this. So that was amazing, And I talked to one of the scientists about this, and he said, Art, you make these exciting models because, you want to make it look good to TV. But if you want a good model of this comet, it will be so highly eroded. If you want a good model, take a basketball, paint it black, and here's your model. Okay? Don't show this stuff. This is all artifacts of, what a light curve is. Well, I'm not going to get into it. Yes?
How much larger is the actual comet?
Yeah, so, there are comets, actually, they are this size, right? But ours is about 2 kilometers by 4 kilometers. I don't know, it's probably a quarter the size of Edmonton. I don't know, how big is Edmonton? Huh? Yeah, 12? 12? So, yeah, third. Yeah. So we built this lander, right? It's called Flay. It has 10 experiments on board. And it has these 3 legs. And the legs are also experiments, to see how... We have no idea, there's an energy absorption device to make sure that it lands gently. It doesn't have any propulsion, so it's not controlled. It's basically a little refrigerator dropped from a spacecraft, except the spacecraft is moving 54,000 kilometers an hour, right, on a body that is, so it's like about and we drop it from a height like if you fly in a jetliner, so it would be about twice that height. So you can imagine you're flying in a jumbo jet, except a little faster, right? And you want to drop this, small refrigerator out of the window, and aim it somewhere, and then it goes. Except the gravity of the comet is so small that it's maybe like a refrigerator made out of styrofoam, right? But it's after you release it from the spacecraft, it's ballistic. And okay, for some other folks here, so I hired an illustrator, a girl from an artist, because I saw her in on a show, art show, and she was really good. She was painting a picture of a new car for somebody who was sponsoring the project from BMW. And the engineer was telling her, yeah, but this front, this grill, that's not what we would want to have. And she was changing this right in front of his eyes. So it was very important. And then she sent me, I told her, maybe there's a job for you. And I just mentioned it in passing. And she sent me an email. Oh, you said that maybe there's a job. And then here's another lesson for you. I never answered the first email like this. Okay? So if you send an email like this to a prospective employer, you didn't get an answer, don't give up. Because my rule is I never answer it because I want somebody who is persistent. Somebody who will, do the job. Not be, oh, could you please, now you write the equation. Okay, solve the equation. Okay, what did you get? What's the error in the equation? I want somebody who'll go and get it, okay? So she sent me another email. I kind of wrote her back, well, I don't know if we have any opportunities. And she wrote me about 5, 6, and then, although I knew after the first email that I want to hire her, okay? So, just a lesson for you, especially in this economy, right? You have to be really persistent, guys. But this is what she drew. We talked to a lot of scientists, and we try to figure out what the surface of the comet is, and help the engineers with the operations. And then, so she drew this cliff. And the scientists were really angry about the cliff and said, no, everything is sort of eroded when you come to the perihelion, it all evaporates and the dust deposits, so it's really smooth, so don't draw this stupidity, okay? And then the engineers were really angry at this, at this German lander, DLR, because they were saying, oh, you're going to scare our management, that we're going to crash, the landing's not going to be successful, so please don't show this chart ever again, so I made this chart for them. Well, Liz did. Okay, and but it was really it was really interesting because I realized she made a series of drawings, and I realized then I'm kind of, there was a guy who used to draw dinosaurs, the first guy who drew dinosaurs. And he affected, and then his drawings got into movies and TV. And now it's, and these were great drawings, except they were wrong, right? But even now, half of us, well, maybe not at Edmonton, but at, at any lower level university, people, think of dinosaurs more of reptiles than chickens, right? And chickens are maybe more representative of what dinosaurs look like. Yeah, because it's drawing. So I didn't want to go wrong because I was actually, I was thinking, if it looks differently, I'm affecting actually people's thinking subliminally, subconsciously. And so this was supposed to be smooth. They were telling me no cliffs, no, draw something more reasonable. And then we get the first picture of our comet, and it starts looking like this, and people, what? What is this? Is it like artifacts in imaging, or is there something problem with our CCD? Invented by a Canadian? CCD, right? I think so, yeah. And so then we start getting better pictures, and this is, you see, 4 kilometers by about 2 kilometers, to answer your question, right? And we see stuff like this. And now, now it gets interesting because this thing spins, I made a 3D print of this, okay? Spins and wobbles, okay? So it spins like this. So how the heck you land on this, And it spins about 12 hours. And it shoots out gas. So, I made this 3D model. Even my dog Lulu was scared, Said, what? What? Said, don't worry, Lulu, you don't have to land on it. And this is answering your question. This is LA. And actually, I never show this picture. I would show it in college. But if I would go to a public, function, I would never show it because I get, oh my God! What's going to happen to us? Is it going to hit right in the downtown? So no. But later, the tweets that come out, Comet is hitting downtown LA. And, so, but you're college, so you understand this precise comparison. So yeah, here's another picture, Liz's picture. We're trying to show, what's going on. So how do you what are the major things that you have to in your design, trying to land on a comet? Dust is a big problem, right? Is it 2 meters of dust? Is it 2 centimeters of dust? Are you going to sink in completely and disappear, right? So that's tricky, And then this is the real picture that we got from a comet. And what do you guys see here? Huh? Somebody was skiing, right? Good conspiracy theory. But really, what is it? What does it look like? You guys probably don't have it, a lot of it here. No, you have it from snow, right? Dunes, right? Because you normally look at the sand dunes, but you guys probably have some snow dunes like that. What do you call them? Do you call them dunes or anything? I don't know. Drifts, banks, yeah. So what is necessary to create drifts and banks? Wind. Do you have wind on a comet? Yeah. Well, you have emanation of gas, but you really don't have surface wind. So, we were thinking about landing on this place, right? Because it looked like one of the very few flat places. And what was one of the theories that scientists come up with? It says, to have dunes, you have to have wind. So she was saying that maybe you have dust, like about 5 meters of dust, and then you have gas trying to sublimate from the inside of the comet, can't get quite through, so it creates the movement. There's wind underneath the dust, underneath, not over it, okay? And basically, if that's the case, you're just going to fall and your spacecraft's going to disappear. So, if you know very little, that's... and there are some areas here, you don't want to hit the boulders, right? And there are a lot of boulders. This was another place we examined for landing. And later we took a close-up picture. It was 358 boulders of the size of this building, okay? Because your resolution improves. You can't land on a slope. You get 30% slope, and this is our lander here. if it goes like this, it would have a tendency to flip over. So that's a problem. So but where do you find a place here for landing? If it has to, the ellipsis has to be about 500 meters, and you can't control it because it's ballistic. And then you have geysers, these jets, right? So, and then later we see these pictures, where and they develop sometimes all of a sudden, and then they disappear like this one disappeared in 19 minutes. So, how do you plan for it? Like this one was also very short-lived, right? And then we take close-ups, and it turns out that sometimes they develop these silos. I can tell you more about it if you'll be interested later on. But also, the other thing is that, look at this, these silos that open up from the jets. Look at the structure, the sidewalls. See, you have these, what dinosaurs, dinosaur eggs, kind of, people call them. And my son asked me, my 14-year-old, when I showed him this, he said, Dad, that doesn't make sense. How can you have dinosaur eggs on a comet if the comet wiped out all the dinosaurs? Yeah, and I created this voodoo duck, with all the possible places to land, where we had a prayer of survival. And then, of course, there's always this discussion between engineers and scientists, right? Where would engineers want to land? Easiest, right? Easiest is what? What's your name? Darren. What's easiest? Flat spot, right? Where would scientists want to land? Most interesting, which is what? Different types of terrain, right? Rocks, boulders, slopes, cracks, crevices, right? So you have that discussion, right? And someday maybe I can tell you at dinner. It was really fascinating. And what was fascinating is an international mission. So these two camps formed. Some wanted to land here, others wanted to land somewhere else. And then I noticed, this camp that wanted to land here, they were all Germans and Italians and Japanese. And the other ones were French, British, and Netherlands. I said, interesting. So we deployed the lander, and the lander took this selfie before. You can see the comet in the back, in the spacecraft in the front. So it was the last picture when it was separating from the spacecraft. And then you have to really strain your eyes here. We got really excited over this picture from the science camera. You see the little dot in a circle? So there's our lander approaching the comet. It was our first picture. And, and then we, expanded it, and there it was, right? Flying. We're very happy. The legs were pointed toward the comet, right? It was slightly spinning. The solar rays on this. So this was very happy time. And then very happy time. This is first picture of the surface from the camera underneath. And we're aiming for this, for right the center of this picture. Not at the round, what looks like a crater, because there were too many boulders there. And here is the last picture before we landed, and everybody's looking, don't let us hit this huge boulder, don't let us hit this big boulder, land in a flat area. And, right. And then the bizarre thing happened. So what was supposed to happen is, we're supposed to land like this. It was the lander was ballistic, right? So it's just approaching on basically the gravity pulls it down, but it goes like at about this speed. It's not like Mars landing, 7 minutes of terror, right? So it goes like this, and then to prevent it from bouncing because it's low gravity, we would fire 2 harpoons into the surface, and then a jet was supposed to press it while the harpoons are firing. Well, guess what? The harpoons didn't work. And guess what? The jet didn't work. Okay? So first, what happened was, we landed, and I was there in Germany at the Mission Control Center, and there are all of these European figures, watching this, and it was an interesting thing about who's going to announce the landing. Because the Germans wanted to announce the landing, which is the lander. European, the guys from Netherlands wanted to announce it because that's where the headquarters is. And, you know, there was the actual camera system is from Italy. So there was this discussion, and they decided that the highest ranking official in the room will announce the successful landing. French flew in their president. So, you know, you can't get away from politics. Okay? And okay, so, you know, here is the guys, you know, television cameras are trained on the operators, and they go, yeah, you know, you've seen these things landing on Mars, and, you know, heterosexual guys hug themselves, you know, hug each other. And then, so they had all that, and then a minute later, we look at next we're supposed to get panoramic, right, of the surface. There were 7 cameras here. So we're waiting for this panoramic, right? And then we get these streaks of things, and black things, and, you know, and dark things, and you just can't understand what the heck is going on. So while everybody's hugging here, you know, and speech is being made, everybody, like, if you see mission control, everybody was like, oh my God, what's going on? You know? And what happened was we all quickly realized that the anchors didn't fire and jet didn't fire, so we bounced, right? And I'm interviewed on CNN live, okay, at this moment. And I just want to tell you why you have to understand basic physics, okay? Because, you know, so I'm on CNN. Next to me is one of the operators talking to Sky News, right? British TV station. And and he's saying, oh yeah, so we suspect that we bounced, the harpoons didn't fire, so you know, we'll be waiting for a few minutes to see where's our, you know, where it's going to drop, right? Because we were thinking so much about gravity on Earth, right? So, you know, you throw something, right? You know, you throw something like this, right? And it falls back. We're so used to this gravity swamping it. And I'm standing there, and I'm quickly, you know, I'm going to have CNN in about 60 seconds. And this is where understanding of the basics have to come in, okay? I'm thinking, okay, so it bounced. Some of the energy will be absorbed. How much? Well, maybe 50%. Well, maybe 70%. It's a lot of dust. So it will be maybe 30%, 20%, 10%. I don't know. So if we're coming at 1 meter per second, so we absorb 90% of energy. So the speed back may be, you know, square root of 0.1, you know, will be 0.3. So it's about 30 centimeters per second. And now, what? How can you figure out when it's going to drop? Have you heard about it? V is equal AT, right? V is equal A times T, okay? So, you know V, 0.3, I figured. You know acceleration G, you know what it is. It's about 100,000 times less than gravity of Earth. So you multiply quickly and you get 3,000 seconds to go, you know, to 0 point, and 3,000 seconds to go down. So it's maybe, you know, an hour. So I'm kicking the guy here because they're showing him from everything. You know? And then I came on, and you know, and I told him, well, you know, we'll have to probably wait for at least an hour because it bounced. And this guy, on the other hand, is kicking me. He says, but, you know, basic physics, right? And you have to do it on your feet, and you have to understand the equation. You have to be sure of this. Understand the fundamentals, right? Okay. So it turned out it was 46 minutes, okay? But it wasn't a minute, 60 seconds, right? So yeah, so, you know, so later you can do this, and you can approximate. This is another thing that college doesn't teach you very well, which is approximate things. You always have exact statement of the problem. And, you know, so, you know, this is later the numbers that we got only, you know, about 10% turned out of the energy back, right? And then, you know, so then you have, you know, the vectors, and I'm not going to go through it there, but you can do it in your head. And, you know, if you look at this, so we're supposed to bounce straight down, but we bounce at 12 degrees. So you have to kind of think, don't depend on your calculator for crying out loud all the time. So 12 degrees, what's cosine of 12 degrees? And you have to kind of have an idea. Is it going to be 0.5, 0.1, or is it almost like 1? Or what is it? You know, because then you can do things. And if you're in meetings and you want to you want to impress people, you have to understand these things. You don't have time to go to the book to your office and read it, and you got to understand the basics, right? So here's very basic vector addition, right? Okay, that's what you need. And then there's ballistic motion here, right? So later on, so I had this CNN interview, and I told him, oh, it will be about an hour. And after we got another signal from Philae, and it was after about 15 minutes, my boss called me from Pasadena, and I heard the sweetest words that any engineer can hear. Because he gave me the biggest compliment that I would ever want to hear. Art, you get to keep your job. So here's Philae approaching, bouncing, and now the comet is rotating underneath, so there's the speed of a comet underneath. So what's going to happen to the Philae, right, when it hits again after an hour? It has, what's the velocity? If it was velocity of this is here, right, you know the velocity of approach, you know that it absorbed 90%, it's about 0.3 meters per second, right? What's going to happen here? What's the velocity here? All right? It's about the same, right? So it's going to get plus, it's going to get a component from the comet, so it's going to get kicked up. And I'm going to run through it because I don't want to get you too tired here with even basic physics. But this is the most phenomenal picture I've ever seen. If you look at it carefully, you see, this is what you see. This is a picture from Rosetta, from the orbiter, where we see how the lander was approaching, right? Coming here, and here's the landing, and then there's no Philae in the landing spot, right? But then somebody, one of the operators, spotted it right here. You see a little tiny dot next to this humongous boulder. It is about the size of this building. And then we didn't think we have to image anything farther away. Right, so we didn't have any pictures of where it went, and we had to calculate from basic physics where it ended up, right? And then we got a picture when it bounced several times. We just got that picture. So it was stuck like a golf ball in a hole, and sideways, so it's like this, and image this. And then it was like the most dramatic moment, for the guys. This shows like a little chipper drill, So we were in this standing like this. Some instruments worked, 7 instruments out of 10 worked, but the drill, man. So it was standing like this, and the drill would, So here's this rock, and the drill would go. They had 30 centimeters of movement, right? It would go like this, and it reached 30 centimeters, but they gave it a margin of 20 extra. So it went, just stopped right before the rock, right? So the drill didn't get any samples. The ovens got only samples that it collected on the way, particles in the air that got ticked up. And the guys who designed it for 5 years, wait for the data for 10 years, were a centimeter away from getting, wonderful papers in Nature and Science. Right? And this is what happened here. You can see we flew right across the whole crater, and we hit the wall there on the other side, and that's where Philae is right now. We're going to fly over it at the end of the mission. And now you can put your glasses on. I have some 3D pictures for you. You can share them with people who don't have them. And make sure that you put them on correctly. Let's see. Yeah, the red's supposed to be on your left, right? If you put them incorrectly and you have blue on your left, you'll start thinking like Americans. And so be careful. If you're thinking right now, maybe everybody should have a machine gun on campus, then you put them in the wrong direction. Maybe you need a bazooka at home for your personal protection. Maybe there's too little violence on television. So switch it over. But you know, here you see the landing site, okay? And you can see that 70% of it was landable and about 3% was not. So there was a lot of stress there. After 10 years, you know, you have a chance to 23% to, you know, for your lander to flip over. Here's the picture of a comet. The minor lobe and a major lobe. There was a lot of hoopla about naming, right? So when we saw this thing, somebody said, "Whoa, space duck!" And it's just stuck. You know, it was 250 scientists in Rome, and it was duck from ever since. You know, it was, the project scientists thought that it's not very dignified to call it a duck. So at the next meeting, he came out and he said, we have a nomenclature here, minor lobe and major lobe. And, you know, in 2 minutes, somebody says, "Yeah, but are we going to land on the head of the duck or on the butt?" So at the next meeting, the next day, because it was a long, 5-day long science meeting, he comes and he says, "Well, the answer is we're going to land on the head of the swan, black swan." Didn't catch on, it was duck, and it stayed as duck. Okay? So, but you can see the morphology here. It's just phenomenal. These are not craters. These are indentations. You know, the gas forms underneath, bubbles up, and you know, and then when the gas escapes in the jets, the whole surface collapses and forms these things. The dust is continuously moving. So very exotic chemistry of the dust. We confirmed that you know, the question which was always of great interest to scientists. Yes, comets could have possibly brought ingredients for life to Earth. All the chemicals, all the compounds are there. You know, formaldehyde is there that would be instrumental in creating ribose, and ribose, you know, leads to DNA. So this was phenomenal. We started understanding how the jets formed, what's the chemistry of the jets. The jets are just really amazing because they shoot out this dust like 700 meters per second. I mean, it's just really violent explosion. We still don't know really how you can collimate the beam. So you tell me, you know, how do you collimate sublimation, expansion into vacuum, right? I mean, you know, it goes out from the surface, and then it, you know, if you puncture a hose, yeah, you know, but here it sublimates into, you know, it's porous, but you would think that it's not going to be, everything's so collimated and such a power, right? So there are still things remaining, you know, questions remaining. Very interesting geology. I'll be able to tell you if you're interested specifically. I'll be glad to tell you more about it. And here is something phenomenal, right? So here's the head of the duck and the body of the duck, right? And so, you know, there was always this question. One group of scientists was saying, we have two comets glued together. The other group of scientists was saying it's an apple core, right? And the reason they also thought that it's apple core is because most of the jets come out from the neck, right? And but now we know that it's two separate comets. So, and how did we figure this out? You know, and it was actually a student that initiated this study. It was really phenomenal. So he took the model of this, right? And for every flat area here, or flattish area, he drew a vector perpendicular to it. And he noticed that all the vectors go into the center either of this body or this body, but not the center of the mutual body, right? So that would point out that there were two bodies, right? So there are some really interesting things. And what is next for Rosetta? So this hasn't been announced yet. So, you know, you're getting some under-the-counter scoop here. But we're going to land again on the Comet, right? 29th of September, maybe 28th, maybe 30th, right around that time. but maybe 29th of September, and we're going to put down the orbiter on the surface for the end of the mission. 29th of September of this year, right? So by that time, you know, we landed first here, okay, where this red dot is, and now we're here, and we're going to land over there, right? We're going to put down the orbiter. If one of you will be in Southern California, you can come, I'll give you a pass, and you'll be able to see live pictures. But you know, it will be spectacular because you know, it's not designed to land. It's a huge orbiter with solar panels the size of a tennis court, right? So as a matter of fact, there's this controversy now for once we decided to land. Now, maybe you can help me out. There's controversy about what to name it. We can't call it landing because it connotates control, right? And if we say, oh, we're going to land and the thing's going to do something else, they'll say, oh, they screwed up. Yeah?
I believe the scientific term is litho braking.
All right. I'll put it forward. And if they pick it, what is your name? Colin, send me an email. And good t-shirt again. Litho braking. So you'll have to send me an email and explain it.
I'm familiar with it at JPL. They do aero braking all the time.
Right. Well, but the litho braking, I think would imply that this is surface braking, right? Yeah. So this is braking by impact. Well, this is a little different because the spacecraft is actually controlled, unlike Philae. So we're going to try to slow it down and just put it down gently, right? But, you know, so somebody said, crash, golly, crash. You know, and it's like they don't know what they're doing, okay? So somebody said hard landing, you know. If you guys have an idea, send me an email. We'll use your idea, okay? But it will be pretty interesting. What is interesting also is that, you know, we try to get the instruments are all on one facet of the spacecraft, one face, right? So you can imagine it's like kind of diving with your head down, you know, and you keep your eyes open, but, you know, on a hard surface. And then what, you know, can we all be able to flip it to save the instruments? Because otherwise all the instruments will get crushed, right? As you're coming down. Yeah?
You're going to land on the head or the butt?
And we're going to land on the minor lobe. And if you're tweeting it out, that's terminology you're going to use, right? Yeah, so as a matter of fact, the reason we're not landing anywhere here is because it seems like trajectories would have to miss, in some cases like by 10 meters, you know, the head of the duck, right? So it's very difficult. So it's a little easier here, right? And you have to land on the equator because it's a little easier to calculate the mutual motion of the bodies. So it will be not very far, actually, from the initial landing site for Philae, but it hasn't been decided yet. So stay tuned. Well, anyway, so to conclude, you know, guys, I hope I convinced you that learning fundamentals is extremely important, okay? So please don't study for grades, okay? And, you know, if you have like 10 chapters for your final, and you read 7, and you haven't still read 3, okay, and you don't know, you know, understand this 7, not just partially understand 10, okay? And, you know, understand this stuff. It makes huge difference, and it will make you a hero in meetings. In meetings, later on, when you'll be at companies, you know, you're not going to be able to go out and look up sources. You have to try, and then, you know, really quickly, we see who understands the basics in these meetings when we talk about all of these issues. Imagine how many issues there are at every decision, right? And then also, you know, you want to learn the human skills, because without them, also your team is not effective. You're not effective, okay? Because if you have 10 scientists and you're only, you know, you only want to have your way, okay? and you don't show the other people that you're listening to them. You know, at Google, they were studying this, you know, how to make the best company in the world. And they realized that it's very important how you conduct the structure of the company and how you conduct meetings, okay? And one of the most important things was how people listen to each other, how they exchange ideas without shooting them down. You know, that's how you progress. And you have to learn that. And to learn that, you know, you have to talk to your professor, you know. You have to try your professor liking you, okay? You know, and to have him like you, what are you going to do? Well, you study and you show him interest in subject and your basic understanding, right? Well, isn't it important?
Absolutely.
Yeah. So, you know, things like that. So I hope you know, I communicated that. And then, you know, if you have that, then someday, you know, it's not going to be me. Somebody's going to land on a comet. You know, it will be you. It will be next generation. So you got to have these skills. And if you have all these skills, you're going to get all your ducks in a row. So thank you so much for listening. Thank you. Yes, and if you, yes, Alan, my handler.
If anybody has any questions about how to get jobs in aerospace or the Rosetta mission, go ahead and ask.
Yes.
How did whoever had to pitch this mission explain it? Because, like, when you went to NASA, did you go to NASA headquarters and say, so we're going to hit a bullet with another bullet, but we don't know what the bullet is shaped like or where it is some of the time. Also, it's going to take 10 years.
Right, right. So you see, very good question, and this is, again, human psychology. So when you sell a mission, okay, you know, you have to decide who you're going to use as your marketing team. You know, NASA doesn't have real marketing teams. But there are some people who are better at it. Like, for example, your professor is excellent. I mean, I listened to his presentation. I was turned on to all this stuff that, you know, charisma, communication skills. You know, we don't want to send somebody who goes, and in 10 years, it will be very long and very difficult, and we will land there. Well, of course, there's only a small chance that we'll succeed. And so please write us a check for $1 billion. You know, so you gotta somebody who, well, as a matter of fact, you know, what we at JPL at NASA, what do we call outgoing engineers? You know the joke about engineers looking at their shoes, right, when they talk to you? So outgoing engineers are the ones who look at your shoes. No, but you see, to answer your question, you have to prepare materials. You have to be good at visuals, right? You have to, you know, understand, like Alan did, understand your sponsor, okay? Who is this person? Once I had a sponsor at NASA headquarters. If it's televised, I should be talking about it. But, you know, who was known for not being very interested in science. He was interested in engineering, not so much in science. Everybody said, terribly difficult person to deal with. So I went to have lunch with him. I went to have dinner with him. I went to have lunch with him. I went to have dinner with him. I asked him, you know, normally people want to talk about their kids, maybe, you know, investments, maybe the degree, his time in college. It was, you know, whatever question I asked was, yeah, I got a PhD from MIT. Okay, and how did you enjoy your time at MIT? That was good. You know, and then everybody was getting that kind of a thing. And then finally, I said, oh, yeah, and my kid went to this ping pong tournament. Ping pong tournament? What was it? And you know, like from then on, I became the best friend, okay? The guy was like heavily into ping pong, okay? And then he started coming to visit me because there's, in Southern California, we have influx of Chinese, and now these phenomenal Chinese, you know, somebody who was like 5th in China, okay, so there's no career possible, but it's like beating everybody 11-0, 11-0 in the United States, you know, and I arranged some, you know, clinics there, and it was like, you know, so it's not only about this, yeah, science has to be terrific, right, but it's also, you know, human factor. Sorry for this long answer to your, yeah.
As a follow-up, did you think it was going to work? Like, did you really believe that you were going to hit the...
So an excellent question, actually. Because, you see, the reason I have a job that I do is because, and the reason you're going to get these jobs is because we engineers are taught to think critically and look for problems, which makes for unhappy marriages sometimes, but it makes you good at a job. So my job is to be very pessimistic and look at the risk and what can go wrong and where you apply the money to mitigate it. Because you can't just build, because if you try to mitigate everything, you're going to have Battlestar Galactica, huge thing, triply redundant. So you can't do that. But actually, privately, we estimated as the possibility of success of a mission somewhere around 20%. It's a really bizarrely difficult thing to do. And I talked to your professors about it. It's a tricky thing. Are you going to build something that costs $2 billion and it's strictly redundant and very well tested? Or are you going to build 10 things and allow two cheaper, much cheaper, single string, and 2 will fail? When you guys are going to be in executive positions soon, these are the kind of decisions you have to make. Yes?
You said you would do something different when you, if you went to college again, or
Yeah,
back?
right. Yeah. So, first of all, I would study differently. Because I study for grades, because I want to have my GPA. Grade point average, you call it something else. GPA? Okay, so I wanted this because I thought I'm going to impress my employer, okay, with my GPA. And I'll tell you, when I get applications from kids, and it says 3.9, and there's nothing else there, circular file, basket, pow. I want to see, I told you, I want to see persistence, right? What are the successful traits, okay, of a person who succeeds? And one of them, most important one, is persistence. You don't give up on problems, That's personality trait. So I was talking to a few of you, you were telling me very bad economy, no good jobs right now, hard to, graduating, hard to. Don't worry about it. Use it as an opportunity. I had shitty jobs. I had really bad jobs, okay? And now, in retrospection, they were excellent jobs. I couldn't get a good job. I was also graduated in times of the downturn. And I was loading cadavers on sleds to test seatbelts, okay? Okay, how bad can your job get, okay? I was testing suspension for cars, by driving for hours over bumps, on a course at Ford Motor Company, okay? And I was doing a lot of stuff like this, and then I was learning from each thing. So get jobs, get bad jobs. You learn how to talk to bosses, to coworkers, you learn patience, you learn, these things that will make you really successful. And, so I, for example, worked on all these, I went to University of Michigan for my undergrad, and I wanted always to work on space, right? So I would, as a little unethical trick, I would interview with a company in Ann Arbor, Michigan, and that was from California, and I would go over there, and I would interview with them, they would fly me over, and then I would go in the afternoon to JPL to say, can anybody interview me, please? I'm interested. And they say, what, you don't have a PhD? Good one. Okay, so, and then I would go again, and I would go again, and they would always, I would have the same chuckle. And then I came maybe 5th time, right? 6th time. And I talking to this supervisor, and he says, what's your experience? And I was telling him I worked on suspension of light trucks, and I did modeling of heat losses in the engine, and I did these, modeling and fast Fourier transforms to calculate the bumps in the road so we can decide we have to repave the roads, and I did this, and He says, oh, so you know about cars? I say, yeah, I know about cars. Oh, we just got yesterday a contract from NASA headquarters to use NASA technology to build an electric car. And it was 25 years ago, right? Okay, when do you want to start? So you never know where it's going to take you, right? So get these jobs, get these internships, and impress the. Also, what you have to do, you have to learn the value of impressing your teachers, having your teachers like you, going to interviews and having people like you, sending nice thank you note, email. These kind of little human things really are important. Yes? Hi. Yeah.
You mentioned that the picture was taken by two Ukrainian scientists,
Right.
one of the best pictures of the comet.
Right.
But then you showed us very high quality pictures. How did you take them before the mapping? So that is my part A. And
Right.
part 2 is that how did you analyze the samples? Did you get them back, or all the testing, everything was done on site? Was there anything? Is there anything coming back?
Right. So to repeat her question, and you correct me if I understood it correctly. The first question was, I showed high-resolution pictures, but what were the original pictures taken by Churyumov Gerasimenko? And I have that picture somewhere, but it's, you take the picture of this comet with the best telescope, and it's still, really fuzzy blob. The only way you know that it's a comet is because it's moving on a certain trajectory, right? And it has certain albedo, right? And it changes, it fades out as it goes farther, and it gets more active. And they as a matter of fact, I saw their original was taken in 1965, so they were actually, pictures, on paper, and not, now they have automatic. The computer looks for any moving objects with the background of the stars. So that was the pictures, 65 or 66, and it didn't look much different than this picture I showed you from a telescope from the ground. Resolution was probably 100 times less, but still it was a bunch of pixels, okay? Part 2 was, she asked how we analyze the samples from the comet. Are there any samples coming back? Or do we analyze them in situ? Is that your comment? Okay, so everything is analyzed in situ. Everything is analyzed by the orbiter and by the lander. The lander had primary batteries that allowed it to survive for 2.5 days, and it had solar panels, right? And the solar panels were supposed to recharge the battery, small battery, and it's supposed to work every 2 weeks. Well, it got in a hole, and it was in a shade, so that part didn't work. But it did work for 2.5 days, and it gave us 7 of 10 instruments gave us results. And everything is analyzed on the spacecraft. So on the lander, for example, the drill didn't work, right? But as the spacecraft was, touched down, there was a cloud of dust came up, and the spacecraft flew through it. So the ovens, because the way it was supposed to work, the drill was supposed to take a sample, transport it to the oven. Oven gets heated up, and when you heat up, you can see then analyze what comes out of the sample, right? So we knew few particles got trapped, and we know what the composition of these particles. On the orbiter, everything is done by spectroscopy, right? We have microwave instrument, we have ultraviolet instrument, and we have infrared instrument, right? So you have to, the beauty of this, the microwave instrument can peer maybe a couple centimeters under the dust into the surface. The infrared instrument is all surface, right? The ultraviolet instrument will show us if there is a CO, if there is a CO2, if there is nitrogen. So that's how we detect these spectra. We have a mass spectrometer on board, and we fly through the coma, and mass spectrometers tells us what constituents we have, especially around 32. It gets very competitive, because you can't separate. There are so many compounds that have atomic mass of 32, but it will be 32.1 or 29.9 or 29.95, and now we know exactly what chemistry of the comet is. Nothing is coming back. Yes?
Just one question about your next mission.
Right.
When you're landing on the other side of when the comet is returning toward us,
Right.
how do you want to achieve the zero related velocity with the comet? Like, we are sending a spacecraft in the opposite direction, yes?
Okay, so you're saying that you're asking how we achieve the compatible velocities between the comet and
So
Why do you say that we would go at retrograde in the opposite direction? Because actually that's what we're going to do, but I didn't want to get into it. It's tricky. Well, yes.
yeah, like in your previous mission, the spacecraft gradually approached it and
Right.
reaching a relatively small
Right.
velocity, yes,
Right.
correct? And then release the.
Right.
But this one is, are you going in the opposite direction? Just
No.
My vision. Like,
So it's it's an excellent question, how we fly around the comet. So let me just tell you in 30 seconds how we fly around the comet. So, comet has very low gravity, so this is a problem and it's a beauty at the same time. The problem is that we have to be very close to the comet to be gravitationally bound. And it's like about 10, 15 kilometers, right? Otherwise, we're not gravitationally bound. The gravity is too low. So actually, imagine this going 50,000 kilometers per hour, and the spacecraft is going here. And then we adjust the speed, and we actually go, because it would take too much fuel to be in circular orbit, so we actually fly in these pyramid orbits. We go, because it's easier to fly straight, right? We just give it a pulse, it flies there, and we stop and we change direction. And each segment actually is 7 days. And why? Because we can do another human thing. Because we can do a trajectory maneuver, on Monday, and we can figure out if everything went okay in the next 5 days, and the operators can have weekend off.
That's going to conclude our Q&A. We're out of time. But I'm going to pass it over to Brad Moon because he's the president of our SPIE chapter.
Good last name.
Appropriate.
And we have a presentation to make.
So one last thing, we would like to thank you for coming and sharing your experience, your knowledge, and your wisdom about the Rosetta Comet landing. On behalf of the University of Alberta, SPIE student chapter, we would like to show our gratitude and present you with an honorary membership.
And I'm really appreciative of you inviting me here and attending the talk, not throwing tomatoes or dust or snowballs at me. Or ducks. And by the way, this university, right? So we should have a test, right? We should have a test. So let's see if you guys paid attention. In one hand, I'm gonna have the comet, model of a comet. In the other hand, it will be something else, not a model of a comet. And you have to tell which one is a comet, okay? On three, 1, 2, 3. Right hand or left hand?
Right hand.
Very good. Excellent, students. Excellent. Your job is so easy.
Thank you very much, Artur, for coming. I really appreciate your coming. I saw your talk in San Diego, was impressed. I insisted that we invite you here, mainly for me. Because you let me hanging last time about life on the Comet. We'd love you to come visit us again. It's an open invitation. Just let us know when you come in here. It's yours.
Well, how about if I invite everybody here for the second landing?
Absolutely. Fantastic. Okay, here's the deal. If you want to be part of the second landing, please register with the SPIE chapter. Okay? Please do that because you can keep a list. We're going to make sure everything goes. And we send it to Artur for approval and we go on. I think, do we need the clearance?
Well, I would have to get. No, actually, for the landing event,
Yes.
I will take care of it.
Okay. All right. Thank you.
You just have to tell them that you came here to see ABC. And here are some bookmarks for you, which have our website. So, if you guys want to check out the website, if you can't travel because you had finals, you'll see some, live streaming of the landing, maybe. So, Alan, maybe you can give it to some close friends.
Everybody's hungry.
The best-looking women in the audience, and tell them, you know what to tell them. What are you going to tell them, Alan?
That I'm doing a human
Yeah, okay.
We're gonna have lunch here, so please help yourself over there to pizza and some drinks.